All right, folks. My phone wasn't loud enough. There he goes. Okay, picking up where we left off in this chapter 5 on simple mixtures. Okay. So where I left off last time was discussing this idea of an ideal solution. And one of the criteria for an ideal solution is that the enthalpy of mixing is 0. So when we mix two things together, no heat is evolved or absorbed. That's one telltale sign of an ideal solution. There's a couple of more, mostly related to the vapor pressure, and you can see that's what I've got going on this graph. So let's talk about this for a bit. So we note that when I have a mixture of liquids A and B in some closed container, it will be in equilibrium with A and B vapor, with the vapor of A and B. Okay, so we can say, suppose the chemical potential of A, and I'll put a star on there, and that denotes, the star tells me it's a pure phase, so that's going to be my nomenclature. And for the gas, okay, and we note that that's going to equal the chemical potential of the pure liquid. So these two phases are in equilibrium with each other. Okay. Similarly, we can say that about B as well. Okay. And B gas is in equilibrium with its liquid as well. Okay. So now if I go and expand on this and write this equation for the chemical potential of the liquid, so that's the pure chemical potential of the liquid, I'm going to get this standard value, so the reference value, excuse me. And this is this equation, that goes the reference value, or the value that's the initial value on the integrand, plus RT natural log, and this works out to be PA star divided by P0, where this PA star is the vapor pressure of pure A. And this P0 is just standard pressure, which is actually 1 bar, okay? So now if we were to expand on this and write the chemical potential of the solution, and specifically now we're talking about the chemical potential of A in this new solution. Okay, well, this equation is going to be modified just a little bit, and it's going to look like the following. It's going to become mu A, I'm going to put a standard, and I'm going to put the star right there because the star tells me this is the pure A. So the chemical potential of A in the solution equals the chemical potential of pure A plus RT natural log of the vapor pressure of the solution relative to the vapor pressure of the pure liquid. Okay? And so if we were to continue expanding on this with B as well, and we also use Dalton's law of partial pressures. I'm not gonna fully derive this, but we would end up arriving at Raoult's law, okay, that says the vapor pressure of the solution is equal to the mole fraction of A times the vapor pressure of pure A plus the mole fraction of B times the vapor pressure of pure B, okay? And then, which means I could expand this equation, or I could write it slightly different for the chemical potential of A in the solution. Okay, it's going to equal the chemical potential standard of pure A, so as if it's by itself, now plus RT natural log of the mole fraction. Okay, so this ratio of P, of the vapor pressure of the solution relative to the vapor pressure of pure A, that's just going to give us the mole fraction, okay? And so this equation is for ideal solutions only. And so this is kind of a major criterion for ideal solutions. So this linear additive way of adding up the vapor pressures, which we know as, let's see here. I can never spell this. Raoult's law. R-A-O-U-L-T. Raoult's law. Okay? So here's a graph of Raoult's law, right? And if we look at this, a mole fraction of A from 0 to 1, and of course I could also make another axis up top here and write that as chi B. And when the mole fraction of A is 1, the mole fraction of B is 0, and the mole fraction of A is 0, the mole fraction of B is 1, right? So now if we look at what we've got going on here, so on this graph, okay, here's my PA star. So that's the vapor pressure of just pure A. And as you can see, when the mole fraction of A is 1 and the mole fraction of B is 0, the total pressure of the solution is just the vapor pressure of A. Similarly, when the mole fraction of B is 1, then the vapor pressure of the solution is just equal to the vapor pressure of B because there is no A. Okay? But now what we see on these graphs are actually the equation here is, so for A, I'll try to write this along it, so that goes chi A times PA star. And then along this line, this is chi B times B star, okay? And so when I add those two together, as is in Raoult's law, I arrive at this total pressure line, okay? And so if a solution obeys this law, in other words, I can just add up the mole fraction weighted vapor pressures, then it's an ideal solution. In addition to this criterion as well, okay? So let's move forward with that, and let's talk about now ideal solutions, and instead of saying real solutions, we call them ideal dilute solutions, okay? So let's look at a real example of an ideal solution here, benzene and methylbenzene, which, could be like toluene, right? And then methylbenzene. Man, I haven't drawn an organic structure like all year. Okay, bam, there we go. So as we can see, benzene and methylbenzene are both really similar. So it's actually not surprising at all that these two make an ideal solution. The golden rule of chemistry, right? Like, likes, like. The golden rule of chemistry. Like, likes, like. So methylbenzene and benzene like each other because they're both very similar. And so now if we were to look at this curve, here the vapor pressures of methylbenzene, and so you can see this would be the vapor pressure of pure methylbenzene right there. And then here on this other side, this would be the pure vapor pressure of just benzene. And then now we add up both of these lines, and that gives us the vapor pressure of their solution. Okay, so what about a real solution or an ideal dilute solution? So for example, carbon disulfide and acetone. So the dotted lines here are the Raoult's law line, R-A-O-U-L-T-S. So these dotted lines are both Raoult's law. And you can see there's actually a region here for acetone where it's following along this Raoult's law line, but then it deviates from that. And you can also see for carbon disulfide, just for a very small addition, so in other words, for a very dilute addition, it's also following the Raoult's law line, okay? So let's expand on that a little bit more, okay? So in an ideal dilute solution, the solute obeys Henry's law, which I'll write down soon. And maybe you remember Henry's law from Chem 109. That's gas solubility. And the solvent obeys, as you might guess, Raoult's law. Okay, so now, for example, here's a fictitious example here. So let's say mole fraction of B. And so we remember that we always have mixtures. So there's A and B in this mixture. And so I could make a new top scale right here, chi A. When chi B is 1, chi A is 0. And when chi B is 0, chi A is 1. And so now what's going on here, we haven't identified which one is the solvent and which one is the solute. But it's generic. We could have either of these as the solute or solvent for this example. Okay, so I'll show you here. So if we look at sparingly small additions of B. So in other words, we're making a solvent with A, and then now a solute with B. So here I'll say B is solute. And I can say B is the solute because most of the time, I mean all of the time really, our solute is going to be the least concentrated thing in the mixture. So it's going to have the smallest mole fraction. And look at this. It's hovering, along Henry's law, this green line. Okay? So Henry's law is just very simple. It's just PB equals chi B times the Henry's law coefficient, KB. So it's just a simple equation, okay? But now if we follow this, so this is B as the solute. So now if I look at PA, for example, it will be chi A. Or really I have to say the solution. So the vapor pressure of A in the solution is going to be chi A times the pure vapor pressure of A. Okay? And if we look at that now here, as you can see, so let's see, like it's not showing us A, it's just showing us B. So you can see now on the opposite case here, we'll say B is now the solvent because at a mole fraction of 1, it's the predominant species in the solution. And A has a mole fraction of 0. And of course, as we move down this line, we're adding A in small additions. So now A is the solute. And you can see in this case, here where B is the solvent now, it's following the Raoult's law line, right up to a certain amount of addition. So like maybe that much, it follows the Raoult's law line when it's the solvent. And now it follows maybe that much of Henry's law when it's the solute. So this is what makes an ideal dilute solution. It's ideal under dilute conditions. So here's a real example of chloroform and acetone. And chloroform and acetone, they're kind of going to interact. They're going to kind of have similar properties. They're both certainly polar. Yes, they're both certainly polar, right? Yep, acetone looks like this. Chloroform is C hydrogen and then the 3 chlorines, okay? But they're still fairly dissimilar. And that's evidenced by the fact that they don't make an ideal solution at all additions. So for example, if I look at acetone here, and then keep in mind, right, mole fraction of chloroform is 0. So that means at this point, the mole fraction of acetone is 1. So we could say on this side, acetone is the solvent. And it's following Raoult's law for, some sparingly small addition. But now when I go, if I keep following down the acetone line here, right, keep following it down, now, aha, look, when now chloroform has become the solvent and acetone is the solute, it's following Henry's law. Okay, so keep track of that. So solute obeys Henry's law, solvent obeys Raoult's law. And in the case of 2 liquids, so with 2 liquids, or really 2 volatile substances, they can switch, right? One can be the solvent, one can be the solute, and that can switch based on how much of it is being added. Now, if we have a liquid and a solid, and we're making a mixture out of a liquid and a solid, that's not going to be the case. The solid is not volatile, okay? And it doesn't do anything. So let me actually back up and say, on Raoult's law here, if solute is a solid, and it makes an ideal solution, then the vapor pressure of the solution is only given by the solvent. So maybe chi A times PA star, and that's it. Because if, let's say, so if the solute is a solid, and we'll call that B, it doesn't have a vapor pressure, okay? So we don't have to worry about it. So this example of ideal dilute solution is really the case with two liquids making a mixture, so two volatile components. Okay, so moving on to liquid mixtures. Okay, so I came up with an equation here earlier. Delta G of mixing equals nRT times chi A, natural log of chi A. So this is just kind of a good little quick review. Chi B times natural log of chi B. Okay. And we also wrote up this equation, delta S of mix, which we know is just negative ddt of this equation. So that's negative nR chi A, natural log chi A, plus chi B, natural log chi B. And we also remembered that when we combine these two things using the equation, delta G of mix equals delta H of mix minus T delta S of mix. This gave us that the delta H of mixture of an ideal solution is 0. All right? So what about ideal? So this is ideal mixing. Well, what about the ideal volume? So delta V of mixing, okay? So question mark. So as it turns out, look, the partial derivative of G with respect to P at constant T, hopefully you remember, is volume, right? So now if I want to talk about my volume mixture, so ideal volume, so delta V of mix is going to be the partial of delta G of mixing by the partial P at constant T. Okay? And if we were to do this derivative, we just get 0 for that whole thing because there is no pressure in here. So when temperature is a constant, well, look, R is a constant and N is a constant as well. So the whole thing just drops out to 0. So what does that mean to have 0 change in volume for ideal mixing? It's not quite what you think it means. It's a little counterintuitive, the derivatives, but once I draw you this picture, hopefully it'll be very intuitive. So suppose we mix two liquids together and they form an ideal solution. And let's suppose I've got 100 milliliters here and 100 milliliters here. Well, 4 years of a chemistry degree should tell you that it makes 200 milliliters. And if that's the case, then it is ideal. So what this delta V is really in reference to, does that delta V, is it any different than this, right? So let me see if I can write this a little bit less confusing. So V final minus V initial, right? And so our V final in this case would be 200 milliliters. Our V initial in this case would be 200 milliliters. So that would give us 0. Now, if we mix 100 mils and 100 mils, and we initially get 200, because we've added 100 and 100 together, but now the thermodynamic environment influences that volume to change relative than what we think it should, then we will no longer have a zero value for delta V of mixing. And that also proves to us that it was not an ideal solution. Okay? So delta H of mixing equals 0 makes an ideal solution. Delta V of mixing equals 0 makes an ideal solution. And the final one I want to talk about are the interactions, so the intermolecular forces between these things. So suppose we had A and B that I was mixing. Okay? So now if we look at their interactions, or in other words, their intermolecular forces, right, the IMF, there are going to be interactions between an A and an A. So I'm going to draw that, and I know it looks like I'm saying a bond. Let's make it like a dotted line, dot, dot, dot. Maybe it's like a hydrogen bond or something, okay? So there's an interaction between an A and an A. There's an interaction between a B and a B. And then, of course, there's also going to be an interaction between an A and a B, okay? And so for ideal solutions, all of these interactions will be equal. So I will say the average A to A INT for interaction is going to be roughly equal to the average interaction between B and B, which is going to be roughly equal to the average interaction between A and B. So for example, suppose all of these interactions are hydrogen bonds. So if A can hydrogen bond to another A, and B can hydrogen bond to another B, then we could conclude that A will likely hydrogen bond to a B, and thus all of those interactions will be roughly the same, and this would be ideal, okay? So the solution becomes non-ideal, or a real solution, or an ideal dilute solution, however you want to think of it, if the following happens. So if the average A interaction is not at all similar to the average B interaction, which then of course would not be at all similar to the average AB interaction. So for example, suppose A is able to hydrogen bond with another A. Okay. But now suppose B cannot do any hydrogen bonding. So suppose it can only do London dispersion. Okay. So maybe an example of this is A is water and B is some greasy alkane, right? Well, then definitely they're not going to interact with each other, right? So the interactions all around are going to be different, and this makes a real solution, okay? And of course, that real solution we could further classify as ideal dilute if the solute follows Henry's law and the solvent follows Raoult's law, okay? What is my next slide? Okay, so continuing along, so I have one last little bit. I left myself one tiny little corner. So now we recognize that delta H of mixing equals 0 for ideal solutions. Well, for non-ideal solutions, there's two cases. There's when delta H of mix is greater than 0. So an endothermic solution. Endo solution, okay? And then, of course, there's delta H of mix being less than 0. So that's an exothermic solution, all right? And if we were doing like a live class discussion, I would break and we would say, let's talk about some examples of these. So you could pause the video and think about some of these examples for yourself. I'm just going to go ahead and tell you about some that I think are really cool. So the one, to me, the easiest one to think about for an endothermic solution is basically exactly what I just described, okay? When you have something aqueous and something fatty, for example, soup, like the stuff you eat, not chemistry, but like let's suppose we're making soup and we've got some water, but we've also maybe thrown a chicken carcass in there, right? We've got some fat that we're trying to extract. And so once we make that lovely soup, and suppose we pull out the chicken carcass and all the stuff, and we've made ourselves, maybe not even soup, but just stock. Maybe we're just making soup stock, okay? So if you think about it, you have to heat that stuff up to get it to mix, right? I don't know a single person who's ever been able to make soup stock by not heating it up. So that's endothermic. You're adding heat to make the fat and the water mix. And then if you've ever taken that stock and put it in your refrigerator, you know that it then separates. It spontaneously separates, and it spontaneously separates because there is a required input of heat to make them mix. And so to get them to mix, you either have to actually do work on it, you actually have to mix them together. That's endothermic. You're providing work, you're doing work on the solution. Or you put it back in the pot and heat it up and make it mix, okay? So that's a really good example of an endothermic solution. Other examples of endothermic solutions are actually cold packs. One of the most popular cold packs is made up of ammonium nitrate. It's got ammonium nitrate crystals in it, and when you break it, there's a little pouch of water that dissolves those crystals. So you're mixing water and ammonium nitrate, and that actually requires an input of heat to get them to mix. And so those become cold packs because now if you, let's say, put it on your body, it's going to take heat from your body to get that thing to mix, to add the required heat to mix. So because it's taking heat from your body, it's going to feel cold. So that's how those cold packs work. Now, coming up with examples of exothermic solution formation is rather tricky. The best example I've got for you is sodium chloride, salty water. And that's because the interactions between sodium chloride and water are much different than the interaction between just sodium chloride and just water, okay? Well, they're pretty similar actually, but there's a much stronger interaction between the water and the sodium chloride. And because that's such a favorable interaction, heat is released when you mix those things, okay? So the last little bit that I want to talk about here before ending this video, the colligative properties. So colligative properties means depending on the collection. And the two best examples of these are boiling point elevation and freezing point depression. Okay? And so here's a really good example of that. Check this out. So we remember chemical potential versus temperature. Where these cross, we get the phase transitions. Okay? Well, as it turns out, when you make a solution, and specifically when we make a solution in which one of the components is non-volatile, so P-vape solution equals PA times Chi-A, so we're dealing with an ideal solution here just to make life a little bit easier, PB times Chi-B. So suppose that B is non-volatile. So that means B could be an electrolyte, it could be a salt, it could be a sugar, okay? But what ends up happening here, because of this, if B is non-volatile, then P-vape solution will always be less than the pure vapor pressure. So that means there's a vapor pressure lowering, okay? And so what that also means is the delta H of vaporization of the solution is actually going to be greater than the delta H of vaporization of the pure liquid, okay? And so the result of that is the boiling point has to increase. If the delta H of vaporization of the solution is greater than the pure liquid, the boiling point has to increase. And so what we could also conclude, and really this is what's driving this, the chemical potential of the solution will be less than the chemical potential of the pure liquid. And you can see that on this diagram here, right? So here is the chemical potential of the pure liquid, and the chemical potential of the solution is reduced, especially when you're adding an electrolyte to water, for example. And now where you look at these things where they cross, you notice it crosses at a higher boiling point, so it's always boiling point elevation. And now you can see that it crosses at a lower freezing point, so that's always freezing point depression, always, for these types of ideal solutions, okay? And so we can write delta T, so the change in the boiling point, okay, that's what this is chi, so the mole fraction of the solute, times the constant, times the constant. I was going to use KB, but we used K for Henry's law, so I'm just going to write it out directly. It ends up being R times T boil squared, so the boiling temperature squared, divided by the delta H of vaporization of the pure liquid. And so all of this right there gives us the boiling point elevation constant, okay? And similarly, the freezing point depression equals the following. K, so it's, chi, solute. And it's a very similar equation, RT squared. And this time it's divided by delta H of fusion. Excuse me. Okay, so each of these in the parentheses give us the boiling point elevation constant and the freezing point depression constant, okay? So I'm just going to show you a couple slides of things that I worked on in my thesis right in this same area. So I looked at how sodium chloride particles in the atmosphere can form clouds. So I did atmospheric physical chemistry. And what I did in my thesis was we actually had a little mini cloud chamber, and we could see how little seed particles, such as sodium chloride, take on water and can grow a cloud. So as it turns out, there's a lot of colligative properties. There's a lot of thermodynamic properties that play there, especially like water interacting with that sodium chloride, dissolving that solid, and then forming a solution. So for example, you can see here on the vapor pressure, so there's a lowering of the vapor pressure. So this is pure A, and let's say that's water, pure water. And so you can see that the vapor pressure of that solution lowers, okay? Also, another thing that's going on here, this graph that I have right here, activity versus sodium chloride weight percent. So that's basically another way of doing mole fraction, except for instead of mole fraction, it's weight percent. So what is this activity business? So we're going to talk about activity soon in the coming lectures. So solvent activity, so I'll write A, solvent, and you can see in this case I wrote AW for water. So solvent activity is the vapor pressure of the pure material divided by the vapor pressure of the solution, okay? So you notice here when I have 0 weight percent of NaCl, the activity is 1.0, right? Nothing has changed, okay? But now as you start adding sodium chloride, it lowers the vapor pressure, and because it's lowering the vapor pressure, it's going to lower this activity, okay? So why is this significant? Well, this line that I have right here is roughly the salinity of the ocean, which is more or less a saturated NaCl solution, about 5 molar, okay? Or like 27 some odd weight percent, all right? And so what you notice here is if you use Raoult's law for the solution, you're going to be way off, right? Raoult's law says it should be like somewhere right there. This black line here is based off of measurement, okay? So we use activity as a means of measuring things that are not ideal. So there's no equation to give us this activity. We just have to do it. We just have to measure it. And this smooth line right here is a polynomial, a fitted polynomial, right? So then often you'll show a fitted polynomial to give you the activities, for this case, for the salty water solution, which is basically a proxy for the ocean, right? The ocean is sodium chloride mostly. Why this is important is because now if you think about, well, what is the vapor pressure above the ocean? Maybe you've never thought about that. I think about that all the time in my research. What is the vapor pressure of the ocean? Well, Raoult's law would tell you it's about 90% of that of what it's supposed to be. And there's another really cool thing. So specifically, water activity is actually just relative humidity divided by 100. Those things are also connected, okay? So for example, when you look at this 0 weight percent, the vapor pressure of pure water is 100% relative humidity, right? So if you have a beaker with just pure H2O and you put a lid on it, okay, it will be 100% relative humidity above that beaker. And of course, as you start adding solutes, that vapor pressure decreases. So Raoult's law would tell us that the vapor pressure over the ocean is supposed to be 90% RH, but that's not true at all. It's actually like 75% relative humidity. And why this is a big deal is because it's the entire freaking ocean, right? It's a huge ass body of water. And if we missed in our global climate models, if we use 90% instead of 75%, that'd be some serious consequence in those global models, okay? So believe it or not, all this crazy thermodynamic stuff can be applied to very big picture important things. For example, the vapor pressure of the ocean, okay? So I'm gonna move on now. I'm gonna stop this video. So I know I lied to you. I said I was gonna do 2 short videos. It's gonna be 3 shortish videos. Okay, folks, I'll see you in the next one.